Okay, so far we've talked about solving problems that are pretty basic. Most of the problems we've been using have just been using the equation Q equals mc delta T. Okay, so remember in our equation Q equals mc delta T. Wow. mc delta T. Q represents the heat either added or removed to the object in joules. M is the mass of the object, typically in kilograms. C is the specific heat capacity, and delta T is the change in temperature, the final temperature minus the initial temperature of the object. Now, this equation is all well and good, but this equation only works for temperature change. Okay, and so you would only use this equation in situations where the object's temperature is changing as you add or remove heat. Now you might ask, well, wouldn't the temperature always change if you're heating an object? No, not necessarily. And so what we're going to do later on is we're going to talk about another equation that deals with things besides temperature change. We're not going to talk about that in this video, though. In this video, we're going to move on to more complicated more complicated problems involving two objects, but still using this equation as a fundamental equation. So that's what we're going to look at right now. So let's talk about the concept of a two-object problem. We talked about before when you have a situation where two objects are in thermal contact with each other, the heat, the overall thermal energy typically tends to flow from the hotter object into the colder object until the two objects reach what's called thermal equilibrium, which is the state where they reach the same temperature and there's no net heat flow between them. And so we're going to make some assumptions in the problems that we're going to be doing. We're going to assume that 100% of the heat that's flowing out of the hot object goes into the cold object. There is actually a problem related to this on one of your thermal physics worksheets where you had to deduce that the energy coming out of the metal was the same as the energy going into the water. And so we're going to make that assumption in these problems. Now that may or may not be a good assumption, because basically the assumption we're making is that there's no heat loss to the surroundings, which may or may not be realistic, but if we make that assumption, it lets us solve some problems. Now, mathematically speaking, what that means is we have two objects, and one of them is going to have heat coming out of it, and the other is going to have heat going into it. And basically the assumption we're making is that those two values are equal. And so the way we're going to write this mathematically is we're going to write Qn, that is the heat going into one object, is equal to Q out, that is the heat coming out of the other object. Okay, now this equation is not quite complete because remember, if heat is coming out of an object, it's typically written as a negative value. And so to get the signs to come out correct, we're going to stick a negative sign in here. So we have Qin equals minus Q out, and this is what we're going to use for two object problems. Okay. So when I talk about Qin and Q out, keep in mind Qin, the left side of this equation, okay, you're talking about the object that heat is going into. Q out refers to the other object. That is the object that is losing heat. So for example, let's say you take a piece of metal and you heat it up so it's really, really hot and you put it in a cup of water. Well, in that case, the heat would be coming out of the heat would be coming out of the metal into the water. And so everything on the left side would pertain to the water, and everything on the right side would pertain to the metal. Okay, so when you're solving two object problems, everything on the left side of the equation should be for one object, everything on the right side of the equation should be for the other object, and so that's how you get a two object problem. Okay, so what we're going to do now is we're going to see some examples of this. Okay, so, example 3. It says a 2 kilogram substance of an unknown metal is heated in a blast furnace to a temperature of 300 degrees Celsius. As soon as you see that, by the way, do keep in mind, as long as we're using the MC delta T equation, we don't need to do a unit conversion to Kelvin. Any equation that has temperature in it by itself needs to be in Kelvin, but our equation has delta T in it, so it can be in Celsius, so we don't have to convert that. It is then removed from the furnace and placed in a very well insulated container holding 2.5 kilograms of liquid miracle tonic. They give us the specific heat capacity of that. At an initial temperature of 70 degrees Celsius, the system reaches a constant temperature of 90 degrees Celsius. How does the heat that flows out of the silver compare to the heat that flows into the metal? And then it says calculate the specific heat capacity of the unknown metal. Okay, so first of all, I can answer this question right away. They are equal. At least that is the assumption we're making. Okay, so when we do Qin equals minus Q out, that's basically the assumption we're making. Now the first thing I'm going to do is I'm going to identify my variables, and so I'm going to identify my variables on this slide, and then I'm going to switch to another slide to actually do this problem. So this is the mass of the metal, okay, and I'm going to label that mass, let's say M, okay, for mass metal. Now, if you want to label things M1 and M2, that's fine, except then you have to remember what is, object 1 and what is object 2. Okay, so I'm going to call that mass metal. I could also call that M1 if I wanted to. So that's the metal that's heated in a blast furnace to a temperature of 300 degrees Celsius. Anytime you're doing a specific heat capacity problem, you're going to be dealing with a final temperature and an initial temperature. And so you need to think, is this the final temperature or the initial temperature? Okay. Read the rest of the problem and see if you can figure out, is this going to be Ti or is this going to be Tf? And hopefully you figured out that this is actually going to be the initial temperature of the metal. And so we're going to label that T metal I, TMI, or T1I if we wanted to label it like that. And the reason it's the initial temperature is because that is the temperature of the metal before it's placed in the container with the miracle tonic. Okay, so that is the initial temperature. So TMI, okay, the temperature of the metal, the initial temperature of the metal. So it's placed, it's taken out of the furnace, it's placed in a container, and the container has this much miracle tonic in it. So I'm going to call that mass. It's a liquid miracle tonic, so I'm going to write ML. Okay, mass of the liquid. Again, you could label this mass too if you wanted. It doesn't really matter what you call your variables, but they do give us the specific heat capacity, and that's going to be CL, okay, specific heat capacity of the liquid, at an initial temperature of 70 degrees Celsius. And again, we don't need to convert that because our equation has delta T in it, so we're fine to keep it in Celsius. Now, if you did convert to Kelvin, you should get the exact same answer. So this 70, I'm going to label that TL, okay, the temperature of the liquid, and that's TLI, because that's the initial temperature of the liquid. The system reaches a constant temperature of 90 degrees Celsius. Now, what does that mean by the system? Well, that means everything. Okay, it means the metal and it means the miracle tonic. In other words, they're saying that the system eventually reaches thermal equilibrium, meaning the miracle tonic and the metal have the same temperature, and so this is actually going to be the final temperature, and we're going to call that TF. Now, I'm not going to call that TMF and TLF because they're in thermal equilibrium. They're going to be the same value, right? That's the point of being in thermal equilibrium. They have the same final temperature. So this is just going to be my TF. My goal is to find CM, the specific heat capacity of the metal. So I don't have enough room on the screen to do this full problem. Okay, so pause it here if you need to write this down, and then I'm going to carry over and solve the problem on a different screen. Okay, so I'm going to erase this, and I'm going to go to the screen over here. And because it's a two-object problem, I'm going to start with my basic equation, that is Q in equals minus Q out. Okay, now in this situation, because the piece of metal is hot and the water is colder than the piece of metal, Q in is going to be everything for the water. So I'm going to take this left side of the equation and I'm going to expand it out. that's going to be the mass of the the mass of the liquid, not the mass of the water. It's miracle tonic, not water. So that's going to be the mass of the liquid times the specific heat capacity of the liquid times delta T of the liquid. And that's going to be equal to minus Q out. Heat is coming out of the metal, and so everything pertaining to the metal is going to be on this side. Again, as far as how do you know which object goes on which side of the equation, honestly, it doesn't really matter. You should get the same answer either way. But just think about, what is the hotter object in this problem? Whatever the hotter object is probably going to be on the right side, on the Q out side, because heat flows from hot to cold. Okay, so that's how I know everything on the metal is going to be on the Q out side. So minus Q out, I'm going to expand that out as M metal, C metal, delta T metal. And really, I'm going to expand it out just a little bit more based off what I'm given. Delta TL is the change in temperature of the liquid. I can actually write that as T final minus T L I. Remember, delta T is final minus initial temperature. They both have the same final temperature. So minus M metal, C metal, and I'm going to do the same thing over here. That's going to be T final minus T M initial. Okay, and even though it looks really bad, at this point all I have to do is plug in numbers and get the correct answer. Okay, so if you look back at the problem, I'm going to pull up my calculator really quickly. The mass of the liquid is 2.5. Okay, so I have 2.5 times the specific heat capacity of the miracle tonic, which is 2000. I'm given the final temperature is 90, and the initial temperature was 70 of the liquid, and that's equal to minus the mass of the metal is 2. The specific heat capacity of the metal is unknown, and so I'm just going to leave that in there, times T final is 90 minus the initial temperature of the metal, which I believe was 300. Yes. Now notice that 90 minus 300 is going to be a negative value. That negative is going to cancel out with this negative sign, and so again, that's why this negative sign is in here, basically to make the signs come out correct, because when you have Q in and Q out should be the same value, but of course Q out should be negative, and so we stick that extra negative in there to make that minus sign go away. So what I'm going to do now is just a little bit of simplification. I'm going to simplify the left side with my calculator. I get 1, 10,000, 100,000 on the left equals minus. I'm going to combine this 2 times 90 minus 300. Okay, so that's minus negative 420 times Cm. The minus sign cancels out. And then I'm just going to divide both sides by that 420. And I get the specific heat capacity of the metal is 238. And that is joules per kilogram per Kelvin. So that is a two-object problem right there. Okay, so pause it there. If you need to look over that, if you have any questions, let me know. Okay, I'm going to clear the screen. And go back to the PowerPoint. Okay, so we're just going to do one more example with the two-object problem. It says, example 4, a small amount of cold water is poured into a cup of hot tea to cool it down, and we're given the masses of both of those. Assume that the water and tea have the same specific heat capacity of approximately 4,200 joules per kilogram per Kelvin. assuming the initial temperatures of the water and tea are 2 degrees Celsius and 40 degrees Celsius respectively, calculate the final temperature of the water-tea mixture. Okay, so I'm going to label my variables. Now in this case, I've got cold water and I've got hot tea. So I'm going to label this is a mass. I'm going to label this MC for the mass of the cold water. Now again, there's no reason why you can't label the masses M1 and M2 and just use 1 and 2 to subscript everything. That's fine. Okay, that's not an issue. I just prefer to not have to remember which one is which. So this is the mass of the cold water. This I'm going to label, let's say it's hot tea, so that's MH. Assuming that they have the same specific heat capacity. So this is basically going to be Cc and Ch. The specific heat capacity of the cold water and the specific heat capacity of the hot tea are the same value. They give us the initial temperature of the water and the tea respectively. So this 2 degrees Celsius, this is going to be T C I, and this is going to be T H I. Again, the temperature of the cold water and the hot tea, and we want to find the final temperature of the mixture. Now, the assumption we have to make here, just because they don't give us enough information otherwise, is we have to assume when they say the final temperature of the mixture, they mean after the system has reached thermal equilibrium. Because if that's the case, then they, by definition, have the same final temperature. Okay, so this is a two-object problem. You can always spot a two-object problem because, well, there's two objects, in this case the cold water and the hot tea. So we're going to be using our equation, Qin equals minus Q out. Okay, so take a look at that, make sure you have everything written down, and I'm going to switch over and solve this on a different screen. Okay, so I'm going to go over here. Again, I'm just going to start with my base equation, Qin equals minus Q out, and I'm going to expand this out. Qin is going to be the cold water because heat is going to go from the hot tea into the cold water. Remember, heat always tends to flow from hot to cold, so I'm going to expand this left side out, and I'm going to get M C C C delta T C. And then on this side, Q out, heat is coming out of the hot water. Okay, so that's going to be MHCH delta T H. Okay, so from here, all I have to do is plug in the values I'm given. The mass of the cold water is 0.02 kilograms. 0.02. The specific heat capacity of both is given as 4,200. Delta TC, I'm going to expand that out and write T final, which I don't know what that is, minus the initial temperature of the cold water, which was 2 degrees Celsius. Again, we don't have to do a unit conversion because these equations don't have temperature, they have change in temperature. As long as we're dealing with the change in temperature, we can be in Celsius or in Kelvin. Okay, so the mass of the hot tea is 0.45, specific heat capacity is 4,200. And then delta TH is going to be T final minus the initial temperature, which was 40 degrees Celsius. Okay, so from here, it's just a little bit of algebra. First, I'm going to simplify my numbers a little bit. I'm going to multiply that 0.02 times the 4,200 and get 84 times TF minus 2 equals minus, I'm going to do 0.5 times 4,200, although to be honest, because there's a 4,200 on both sides, we could have canceled that out if we wanted to. It doesn't matter though. So those two combine to minus 1890 times T final minus 40, and now I need to distribute because I need to combine my TFs together. So that is going to be 84 TF minus 84 times 2, okay, which is minus 168. Remember, when you're multiplying with parentheses, you just multiply one at a time, like this. And on this side over here, I get negative 1890 TF. Be careful here because this is a very common mistake. This negative times this negative is going to give me a positive, and that's going to be a positive 1890 times 40. Just type that into the calculator. This can be plus 75,600. And now all I have to do is combine my like terms. I'm going to add this value to both sides. I'm going to add this value to both sides, and then I'm going to divide. So you should get, let's see, what is that going to be? 1890 plus 84 is 1974 TF is equal to, and by the way, as you're doing these problems, there's an easy way to see if you made a mistake. Just think about what it is you're doing. If you're putting cold water into hot tea, then you would expect that the final temperature of the water is going to be higher than it was originally. And you would also expect that the final temperature of the hot tea is going to be less than it was originally. That's just kind of common sense. Okay, so once you get an answer here, you can easily check to see if it makes sense. So don't rush too much through these problems. So I get TF equals 38.4 degrees Celsius. Okay, now the original temperature of the hot tea was 40 degrees. It's a little bit less than 40 degrees, which makes sense because we added some cold water to it. And so far this problem looks like it makes sense. So there you have seen two problems with two object problems. Now, we have not done phase change yet. And so if you look at what we have here, we have a MC delta T on both sides of the equation. That's because in all of the problems we've done, we've only dealt with temperature change and heat with temperature change. And so in the next video, we're going to talk about what happens when you have a phase change added. And what we can see is you can still do two object problems, but they can actually get way more complicated when you add in the possibility of phase change. So this is just a basic two object problem with MC delta T. You should now be able to work on your next worksheet. Please let me know if you have any other questions.